All right, let's get right into it. Welcome to this explainer where we're going to demystify the somewhat messy world of laboratory mathematics. You know, we often think of science as this pursuit of exact, absolutely perfect answers, but the reality is actually so much more fascinating. Today, we're going to reveal how scientists use error margins, rounding rules, and significant figures not to obscure their results, but to tell the absolute, unvarnished truth about our physical world.
To truly understand this mathematical language of honesty, we'll be tracking the exact chronological journey a scientist takes. We'll hit 5 key stops: the reality of measurement, how errors multiply, using calculus in error measurement, the strict rules of rounding, and finally, decoding significant digits.
Before we crunch a single number, we really have to establish a core philosophical truth in science. No measurement is absolutely perfect. Never. Our fundamental limitation always starts with our instrument's least count. That's the smallest tick mark on your ruler, or the smallest decimal on your digital scale. It represents the baseline of uncertainty in literally any experiment you will ever do.
Okay, let's jump right into Section 1, the reality of measurement. To report data honestly, we have to distinguish between two totally different concepts. First, you've got the absolute error. That's just your raw difference in units, like saying, hey, we might be off by exactly 0.1 centimeters. But then there's the percentage error, which honestly is way more crucial. Percentage error tells us the contextual weight of that mistake. Think about it. Being off by 0.1 centimeters on a 1-kilometer suspension bridge? Basically nothing. But being off by 0.1 centimeters on a microscopic computer chip? That is an absolute disaster.
So applying this to a real measurement is pretty wild. If our instrument's least count is 1 millimeter, well, that creates a 0.1 centimeter absolute error right out of the gate. We have to carry that baseline uncertainty forward. And here's the golden rule. Whenever we add or subtract distinct measurements, those absolute errors strictly add together. Basically, our window of uncertainty only ever grows.
Which brings us nicely to Section 2, how errors multiply. Because what happens when we take those flawed baseline measurements and actually plug them into complex physics equations? Well, we run into the domino effect of power functions. When a measurement is squared or cubed in a formula, its percentage error doesn't just sit there quietly. No way. It multiplies by that exact exponent. So if a variable is cubed, its fractional error is multiplied by 3. The math rapidly amplifies our slightest little inaccuracies. Imagine holding a physical sphere. Say you measure its radius as 5 centimeters, but you're unsure of its true boundary by just 0.1 centimeters. Seems tiny, right? That's just a 2% relative error. But because the formula for volume relies on the radius cubed, that tiny 2% absolute mistake absolutely explodes into a massive 6% total volume error.
We see a really similar compounding effect when we track a moving particle. Kinetic energy is half the mass times velocity squared. If we have a 2% error when measuring a 5-kilogram mass and a 1% error measuring the 10 meter per second velocity, we have to systematically combine them. Because velocity is squared, that 1% error instantly doubles to 2%. We add that to our 2% mass error, and boom, we're looking at a 4% total error margin for the kinetic energy.
Now, simple algebra works great for standard power functions, like volume or kinetic energy. But as we know, science often deals with much messier realities. That leads us to Section 3, calculus in error measurement.
So what do we do when our formulas aren't just neat little powers? What if we're dealing with inverse relationships or complex fractions? Well, we have to upgrade our toolkit to make sure we aren't underreporting our uncertainty.
For non-power functions, like the classic lens formula where 1 over the focal length equals 1 over the image distance plus 1 over the object distance, the brilliant trick is to use direct differentiation. By taking the derivative of the entire equation, we break it down into its differential parts. It's like taking apart an engine to see exactly where the leak is coming from. It mathematically isolates the changes so we can track the error precisely.
To put that into perspective with a practical example, if you're engineering a parallel resistance circuit, you'd use a very similar inverse formula. By applying direct differentiation to two resistors, say one at 30 ohms and one at 60 ohms, both with a 1 ohm margin of error, we can confidently calculate a 2.8% total error margin. And let me tell you, finding that 2.8% isn't just some chalkboard exercise. For an electrical engineer, that is literally the difference between a perfectly working device and a blown fuse.
So, we've successfully tracked all these messy errors through our calculus. Let's move on to Section 4, the rules of rounding, where we clean things up for the final report.
Rounding trims the fat from our sprawling decimals so our answers reflect the true precision of our tools. But to avoid systemic bias, scientists follow a very strict, impartial set of rules. Most of these you probably remember from grade school, but pay close attention to the specific rules for when a number ends exactly in a 5.
For the basics, the logic is totally straightforward. Trailing digit clearly below 5, like the 4 in 1753.34, just drop it. Above 5, like the 6 in 1753.86, we decisively round up that preceding digit to a 9. Simple enough, right?
But hold on, what happens when a value sits perfectly, exactly in the middle, like 185.50? If we always defaulted to rounding up, our data over thousands of measurements would artificially inflate. We'd introduce a systemic bias. So we rely on the odd/even rule, always round to the nearest even number. Meaning 185.50 rounds up to 186, but 184.50 actually rounds down to 184. It's a brilliant little trick that ensures statistical fairness across massive data sets. And finally, we arrive at Section 5, decoding significant digits. Significant figures, or sig figs, dictate the resolution of our honesty. They define exactly which digits were genuinely measured by an instrument and which ones are merely mathematical placeholders just keeping the decimal point in the right spot. Any non-zero digit obviously counts, but the true test of a scientist's understanding is knowing exactly what to do with a zero. Is it just a spacer, or does it represent a perfectly measured reality? Look at how this works in practice. 700 seconds has only 3 significant figures. But 700.00 seconds? That has 5. Those trailing decimal zeros aren't just redundant fluff. They are the scientist aggressively proving their exact precision, literally communicating, hey, we measured this confidently all the way down to the 100th of a second. Ultimately, everything we've covered today, from least count baselines to calculus error propagation to the odd-even rounding rule and sig figs, these aren't just arbitrary math hurdles to clear for a high school quiz. They're the essential vocabulary of scientific integrity. They ensure we never overpromise on our understanding of the physical world. So the next time you see a highly specific statistic in a headline, ask yourself, are those numbers actually telling the whole truth, or are they hiding their uncertainty? Thanks for hanging out with me for this explainer, and remember to always keep questioning the data.